Characterization of planar graphs. Recap of previous lecture, we have discussed planar graphs, that is the plane graph embeddings, dual graphs, Euler's formula for plane graphs and regular polyhedra. Content of this lecture, we will discuss the characterization of planar graphs, that means yet another characterization of planar graphs beyond the Euler's formula. We will also discuss subdivision of a graph, minor of a graph, Kuratowski's theorem and Wagner's theorem. Characterization of planar graphs. If we recall, we have used in the previous video the Euler's formula, which is n minus e plus f is equal to 2, and we have seen using this particular Euler's formula that K5 and K33 are not planar. Now, if G contains a non-planar subgraph, then G is not a planar, that is G is non-planar, that we will see as the another characterization of a planar graph. That means you know that a planar graph, if it has the subgraph of a planar graph, is also a planar. Similarly, if the subgraph of a graph is non-planar, then obviously the graph is not a planar graph, or graph is non-planar is another characterization that we will see. For example, we see that this is K5, K5 is non-planar. Now, if we add some vertices and we form another graph where this K5 is a subgraph, then this entire graph G prime, a bigger graph, is also non-planar. Why? Because this K5 is a subgraph of this particular graph. So, hence any non-planar subgraph if the graph G contains a non-planar subgraph, then G is also non-planar. This is the necessary condition for the non-planarity that we will see in further theorems. Furthermore, if we take G5, if we take K5 and we take the subdivision of this edge, so subdivision of the edge, we will obtain another graph, and from a non-planar graph, if we obtain a subdivision of a non-planar graph, then that particular graph is also non-planar. All these things we will discuss as the characterization of a planar graphs. Let us see about the elementary subdivision. An elementary subdivision of a non-empty graph G is a graph obtained from G by removing an edge, that is E having two endpoints u v, and adding a new vertex w and the new two edges, that is u w and v w, meaning to say that if there is an edge with the endpoints u v, so instead of that, what we will do is we will remove this particular edge and we will add a vertex w with the endpoints u and v, and we will add two edges, that is E1 is equal to uw and E2 is equal to wv. This is called the elementary subdivision of the graph. So, for example, if this is the graph, now this particular edge we will consider. What we will do is we will take this graph without this particular edge and we will add two more edges plus one more vertex we will add, and we will add 2 more edges, that is UW and WV. So, this is called the elementary subdivision of the graph G. Now, subdivision of a graph G is a graph obtained from that graph by sequence of 0 or more such elementary subdivisions, that is called subdivision of a graph G. Let us take a graph G and obtain a subdivision of a graph G, that is G3, by applying more than one such elementary subdivisions in this particular graph G. Now, if we apply the subdivision in this particular edge, and we will introduce a vertex, and this particular edge will be replaced by 2 different edges. So, let us say that this is edge E. So, we are replacing it by 2 more edges E1 and E2 using the elementary subdivision. Similarly, this particular edge we are further subdividing it. This particular edge E1 we are further subdividing it into E1 prime and E1 double prime. This is elementary subdivision, and we will introduce this new vertex into it, obtaining another graph, that is G2. And now, if we see this particular graph, we will obtain, and here if we take this particular edge and we will replace this edge E3 as E3 prime and E3 double prime, and also introducing a new vertex. So, we obtain a G3. So, G3 is basically a subdivision of a graph G. Now, another example of a subdivision of a graph is a graph obtained from it by replacing the edge with a pairwise internally disjoint paths. That is basically here they are also called as internally pairwise internally disjoint paths. So, if we take the graph K33 and if we apply this particular subdivision of this graph, we will obtain another graph from K33 by subdividing these edges, this edge, this edge, this edge subdivision, this edge subdivision, this edge and this edge. So, let us take this particular graph and apply the subdivision. So, from K33 we obtain this particular graph G after doing the subdivisions. Hence, this graph G is a subdivision of the graph K33. So, any subdivision H of a graph G is a planar if and only if G is a planar graph. So, if we obtain a graph, let us say H from G using the subdivision, and that G let us say is K5 or K33, then any such subdivision which we obtain out of these K33 and K5 hence basically are non-planar, and their subdivisions will basically prove that a given graph H is also a non-planar. So, for planarity condition, so any subdivision H of a graph G is planar if and only if G is planar. So, this will characterize yet by another way the planar graphs. So, remark 2 says that if graph G is a subdivision of K5 or K33, then G is non-planar. Why? Because we have earlier already proved that K5 and K33 they are non-planar, and any subgraph which we obtain of the as per the subdivision of these graphs will also be a non-planar. Now, remark 3 says that if a graph G contains a subgraph that is a subdivision of K5 or K33, then G is non-planar. Again I am repeating, if a graph G contains a subgraph that is a subdivision of K5 or K33, then G is a non-planar. So, with this let us see the famous theorem for the characterization of planar graph, that is given by Kuratowski's theorem. Kuratowski has given a theorem in 1930. The theorem is stated as the graph is planar if and only if it does not contain a subdivision of K5 or K33. So, let us take the example of the statement of this particular theorem. So, in the example let us take a famous graph that is called a Petersen graph. Now, we will obtain, so we will show that this Petersen graph contains the subdivision of K33, and as per the statement of a theorem, if this particular Petersen graph contains a subdivision of K33 which is non-planar, so hence that graph will also be non-planar. Now, the subdivision is, if the subdivision is planar, then only the Petersen graph can be planar, but we will show that the subdivision of Petersen graph is K33 which is non-planar, hence the Petersen graph is non-planar. So, to show that Petersen graph is non-planar, let us find out, let us see the bipartite graph 1, 3 and 7. Let us take these vertices on one side of a Petersen graph and the other side of a Petersen graph. Let us choose 2, then 8 and then 4. So, you can see they are independent sets, 2, 4, 8, they are independent sets. Let us draw the bipartite K33 graph. So, as far as 2, 8, 4 is concerned, we will draw an vertices, and the other side we will draw 1, then 3 and then 7. Let us draw the edge between them. 1 and 2 is an edge, so that edge we have taken up. Then from 1, 2 and 3 there is an edge, 2 and 3 there is an edge, so we added the edge. Then 3 and 4 are having an edge, so this edge we have added. Then 3 and 8 we have an edge, so this edge we are going to add. Then 2 and 7 we have an edge, we will place an edge here in our bipartite graph. Now, as far as 1 and 4 is concerned, 1 and 4 they do not have an edge, but we will take the subdivision of 1, 4 with 5 to be included as a subdivision. So, 1 and 4 they have an edge with a subdivision at 5. So, we will place an edge between 1 and 4 with 5 as its subdivision. Similarly, 1 and 8 will have an edge with a subdivision at 6. So, 1 and 8 is having an edge with a subdivision at 6. Now, we will take 7 and 8. Now, 7 and 8 is having an edge with 10 as its subdivision. 7 and 8 is having an edge with 10 as its subdivision point. Now, 7 and 4 will also have an edge with 9 as its subdivision. So, we have obtained K33 as a subdivision of So, this particular graph contains, this particular graph Petersen contains subdivision of K33. Now, we know that this particular Kuratowski's theorem says that a graph is planar if and only if it does not contains a subdivision of either K5 or K33. Since it contains a subdivision of K33, hence it is not a planar graph. So, Petersen graph is non-planar by Kuratowski's theorem. We have again shown this in this particular figure. We will take another example to basically obtain a subdivision of K33. So, if you let us see it again. So, let us take red particular dots as basically one side of the partite set, that is K33, and all the green points as the other side of the partite sets. Now, let us add an edge between 1 and 6, there is a direct edge. Between 1 and 2, there is a direct edge. Between 1 and 5, there is direct edge that we have included. Now, between 8 and 2, between 8 and 2, there is a edge with 3 as its subdivision. Similarly, 8 and 6 is a direct edge. Then 8 and 5 is having an edge with 10 as its subdivision. Now, we will see the 9 and 6 is having a direct edge. Then 9 and 2 is having an edge with 7 as its subdivision. Similarly, 9 and 5 is having an edge with 4 as its subdivision. Hence, we have shown that this Petersen graph contains a subdivision of K33 according to the Kuratowski's theorem. This particular K33, which is a non-planar, it contains a subdivision as a non-planar graph, hence it is not a planar graph as far as the theorem is concerned. Now, let us see another way of characterization of planar graphs by the way of edge contraction. Let us revisit the concept of edge contraction, which we have earlier shown in the video lecture. So, if this is the original graph and let us choose a edge E, by contraction means we will remove this edge and join these particular vertex U and V, they will become one vertex. That is called edge contraction, and all the other incident edges will remain intact. So, this becomes basically the loops, this becomes the multiple edges. Between these two endpoints. If we remove them, the extra edges, we will obtain a graph without multiple edges, that is a simple graph which we obtain out of the edge contraction. Edge contraction sometimes we will write down using dot also or using another such notations. So, let G be a graph and E be an edge in a graph with its endpoints as UV. Suppose W is an vertex in V, now contracting an edge E in G results in that edge contracted graph obtained from the graph by removing that edge, replacing these vertices U and V with a single vertex W, that we have done. Then the vertices, then with the vertex W is adjacent to the neighbors of U and neighbors of V. So, all the adjacency relation of U and V are preserved by W, hence these particular edges are added. So, that is called edge contraction steps. So, having understood the edge contraction, let us define the minor of a graph. Let H is called the minor of a graph G if it can be produced from G by successive application of the edge contraction or by deleting an edge or by deleting an isolated vertex. So, with these three reductions, if a graph which is obtained out of a graph G, which is that graph is called a minor of that graph. So, graph G is a minor of itself if none of these operations are performed. Now, every graph that is isomorphic to a minor of graph G, also called a minor of graph G. Now, let us see non-trivial cases. Now, here we will show that this particular graph G has K3 as a minor. So, to show that, to obtain a minor of this particular graph, let us perform one of these steps. So, let us choose this particular edge E and delete this edge. So, this particular vertex will remain an isolated vertex. Now, perform another operation called deleting an isolated vertex. We will obtain this particular graph. In this graph, we will select this edge and perform the edge contraction. So, when we perform the edge contraction, the multiple edge will come, and let us delete this particular edge, so that we will obtain a K3 as its minor. So, the graph G we have shown has K3 as the minor. Now, in this particular picture, we will take this edge contraction example. Here, if we contract this particular graph along this particular edge E, we will obtain the edge contraction of that graph on the edge E, that is called edge contraction. So, let us see that from a graph G, if we perform the edge contraction around this particular edge, we will obtain this graph, and again we will perform the deletion of this particular edge, we will obtain this graph, and then perform another contraction, this edge contraction, we will obtain this particular graph. So, this graph is called K13, hence this graph G contains a minor, or we can also state that K13 is a minor of graph G, or G contains K13 as the graph minor. With this, let us state the Wagner's theorem given in 1937. A graph is planar if and only if neither K5 nor K33 is a minor of that graph G. Let us take the example of a Petersen graph, that is well known graph, and try to obtain the minor of its minor as K5 or K33. Now, for Petersen graph, it is easy to obtain a minor K5. So, we will choose to obtain K5 as the minor of Petersen graph, because this particular graph looks like a K5 or K5 as its minor. So, we will choose this K5, and let us show that this Petersen graph is, or K5 is a minor of this Petersen graph. So, let us perform these steps. First, we will choose the edges, these edges where we perform the edge contraction. On Petersen graph, following edges we have chosen E1, then E2, then E3, E4, then E5. 5 different edges. When we contract edge, when we perform the edge contraction, we will obtain this graph, that is nothing but a Petersen graph. So, this is K5 as a minor of Petersen graph. Since Petersen graph has K5 minor, therefore, Petersen graph is non-planar according to Wagner's theorem. So, same thing again, we are representing it. Let us say that this is the Petersen graph. We will perform the edge contractions on different edges shown in the red color. The resulting graph is isomorphic to K5. So, Wagner theorem has proved that this Petersen graph is non-planar. So, we have seen that Petersen graph is non-planar by two different ways, that is by Kuratowski's theorem and Wagner's theorem. Now, let us see the difference between these two theorems, that is given by Wagner and Kuratowski's. Wagner theorem is stated in 1937, much later than Kuratowski's theorem, which says that a graph is planar that will characterize that it has no K5 or K33 as its minor. Kuratowski 1930 stated that a graph is planar, that is equivalent to saying that it has no subgraph, that is the subdivision of K5 or K33. Now, this subdivision of H can be converted into H minor by contracting all but one edge in each path formed by the subdivision process. Let us see this particular example. So, if this is the subdivision, we can convert into H minor by performing the edge contraction. So, when we perform the edge contraction, this will become one particular vertex. Then again we will perform the edge contraction, this edge contraction, then this will become one, and then again one more edge contraction. So, this will become one edge between, and hence we obtain the K33 as its minor. But an H minor cannot be converted into the subdivision of H. So, for K5 and K33, if G has more than one of these as minor, then it has more than one of these as the subdivision. So, conclusion, in this lecture we have discussed the elementary properties of subdivision and minor, Kuratowski's theorem, Wagner's theorem, and also proved the non-planarity of Petersen graph. Thank you.